A worst-case volcanic supereruption creates a disaster of almost unimaginable scale. Millions of tons of dark, heavy ash shoot halfway to outer space, then collapse outward at hundreds of miles per hour. This highly charged pyroclastic wave swallows entire landscapes, shorting out power grids across half a continent. The local destruction is only the beginning. That ash and sulfur dioxide form a chemical veil in the upper atmosphere, blocking out the sun and plunging the planet into a multi-year volcanic winter. In 1816, a much smaller eruption at Mount Tambora caused global temperatures to drop, leading to worldwide crop failures and massive starvation. A supereruption would be at least 10 times more powerful. The source of this apocalyptic threat is an otherwise peaceful American tourist destination, Yellowstone National Park. You don't see a traditional volcanic mountain when you visit, because the last time Yellowstone experienced a supereruption, it blasted out so much material that the ground literally collapsed. The volcano fell in on itself, leaving behind an invisible 32-mile-wide crater called a caldera, completely hiding the threat below. Because of the boiling mud pots and steaming geysers on the surface, a popular myth has taken hold. People often picture Yellowstone sitting directly above a giant bubbling ocean of glowing liquid lava that is constantly building pressure and waiting to burst. To understand if this apocalypse is actually imminent, we have to throw out the Hollywood imagery. We need to look past the surface and map the precise geological machine hiding beneath our feet. Scientists can't simply drill deep enough to see what is down there, so they rely on earthquakes. By measuring how thousands of seismic waves change speed and direction as they travel through different materials, geologists use a technique called seismic tomography to build a 3D CT scan of the Earth beneath the park. This graphic shows a cross-section of the Earth's crust directly under Yellowstone. The seismic scan reveals the first major component, a shallow magma reservoir beginning about 5 kilometers below ground and extending down to roughly 17 kilometers. Beneath that shallow zone sits a much deeper basaltic reservoir. Fed by a massive plume of heat rising from the Earth's mantle, this lower chamber sits between 20 and 50 kilometers deep. When we map them together, the scale of this lower chamber is enormous. The deep reservoir is roughly 4.5 times larger than the shallow one above it. The discovery of this immense, layered plumbing system proves the volcano operates as a highly complex geological machine, far different from the popular image of a simple lava lake. To address the liquid magma myth directly, we have to look at what is inside these chambers. They are what geologists call a crystal mush, a hot, rocky sponge made almost entirely of solid crystals, with only small pockets of trapped fluids and gases. This chart illustrates the exact ratio of solid rock to liquid magma in the shallow reservoir. Based on the seismic data, scientists estimate that this upper chamber contains only 5 to 15% actual liquid melt. Down in the deep reservoir, despite its massive size, the liquid fraction drops to roughly 2% melt. For magma to become mobile enough to erupt, the amount of liquid generally needs to cross the 50% mark. Right now, Yellowstone sits far below that line. The volcano physically cannot erupt in its current solid state. The only way to trigger a supereruption is to melt that solid mush. That requires a massive injection of new, boiling basaltic magma surging up from the deep reservoir to heat the upper slushy and turn it into a liquid. Because Yellowstone's magma system lacks the liquid fraction required to move, it is locked in a highly stable state. It is a sleeping geological giant, completely incapable of acting like a ticking bomb waiting to go off tomorrow. That leaves one crucial question. If a massive injection of EEP heat did occur, how long would it take for the crystal mush to melt and trigger an eruption? To find out, scientists examined the aftermath of Yellowstone's last supereruption. They sliced open ancient ash crystals and analyzed their microscopic layers, which act exactly like tree rings, recording the chemical conditions of the magma chamber over time. The timeline they uncovered is astonishingly short. Once fresh, boiling magma injects into the reservoir, the system can reach an eruptible state in only a few decades, rather than thousands of years. While that timeline is remarkably fast, the mathematical odds of such an injection happening in any given year remain incredibly low, about 1 in a million.
Furthermore, we would see it coming. If the slushy began to melt, the intense pressure would cause the ground above to swell significantly. We would detect massive localized earthquake clusters and measure sudden spikes in volcanic gas emissions across the park long before an eruption could even begin. Yellowstone is a restless, colossal geological engine, but because its magma is mostly solid, deeply buried, and closely monitored by sensors every single day, it is a force that demands our respect, not our panic.